Hi guys, and welcome to the video on mutually exclusive or not events. So in this video, we're going to talk about events that can not happen together or events that can happen together, and then we're going to calculate the probabilities of both of those. Mutually exclusive events let us talk about impossible events or calculate other probabilities, so that's why we're doing this. And then you'll know you're successful when you can calculate the probability of one of two events occurring based on their mutually exclusiveness. So, please make sure you get this formula down. Two events are considered mutually exclusive if they cannot both be true. So the formula for that is the probability of A or B happening is that you add the probability of A and the probability of B together. If you saw in the video for 6.3, there were some problems where I did this um, kind of instinctually. Mutually exclusive events um, happen all the time in probability. Lots of times, like when you're calculating different outcomes on a single die roll, it's mutually exclusive. You can't have a die turn up a 4 and a 6 at the same time. So it has to just be one of the two. So a lot of times we can quickly just add those two probabilities together in order to calculate the probability of one or the other happening. Um, a quick word about union and intersection. So when we talk about mutually exclusive events and we use Venn diagrams, we need to understand the difference between union and intersection. So the intersection of two events represents the probability that the events both happen. So in a Venn diagram, it's that little section in the center. The union of two events represents the probability that one or the other event happens. But the intersection counts for that, okay? So if A and B happens, well, then either A or B happened. So the probability of the union of two events is usually 100% of the probability for both of them. It's either A or B. So you can see those illustrated on the two Venn diagrams down below. Intersection on the left is and or is on the right. So mutually non-exclusive events. So non-mutually exclusive events are events that can both be true at the same time. So for example, you roll a die. The probability that the die shows up as an even and a prime number are two non-mutually exclusive events. Because 2 is both prime and an even number. It is possible for the die to do both at the same time. It is possible for the die to come up both even and prime. So the probability, okay, and if we look back to the Venn diagrams on the previous slide, that probability that we're calculating is the probability of them both happening. So to calculate this probability, if you're going to calculate the probability of one or the other happening, okay, you're going to calculate the probability of A and B added together, but then you have to take out their overlap because we are looking for the probability of one or the other, but not both. So I'll say that again. For the probability of two mutually non-exclusive events, if you're calculating the probability of one or the other, that's what the formula shows. You are calculating the probability of both happening, but you have to take out the probability of them happening simultaneously. So let's do some examples here. Or using a Venn diagram, we'll get into examples pretty quick here. A Venn diagram can be used to represent a situation and then calculate the probability of a random choice being made or occurring. So in this Venn diagram here, 17 students take chemistry, 22 take biology, and then 15 students take neither or both. Right now I can definitely see if only 8 take chemistry and only 13 take biology, that means 9 take both combined together. And since 9 take both and 15 take neither of both, that leaves 6 taking neither. But the total here, 6, 8, 9, 13, should sum up to 45. Oh, excuse me, the 17, 20, 17, 22, and the 6 adds up to 45. Excuse me. Wrong addition. Because the 9 count for both. Okay, so let's continue. So examples of, again, so I just wanted to be super clear on what the examples of mutually exclusive versus not is. So mutually exclusive events happening would be like turning left and then turning right are mutually exclusive because you can't do both at the same time. You can do one after the other, like really quick, but you can't do it at the same time. Tossing a coin, heads and tails are mutually exclusive events. A coin either turns up heads or it turns up tails. You may have the absolute 1 in a million situation where the coin turns up nothing, but it either turns up heads or tails. It cannot do both. Um, in cards, for example, kings, drawing a king versus drawing an ace would be mutually exclusive. If you do a single draw, you can't have a card turn up to be a king and an ace. Um, Other things that are non mutually exclusive would be like turning left and scratching your head. Those things could happen at the same time. And then kings and hearts, because you could draw a card that is both a king and a hearts. We call it the king of hearts. So you can have those kinds of mutually non-exclusive events. Okay, so let's take a look at some examples here. A card is chosen from at random from a pack of 52 playing cards. What is the probability of a king or a queen? So these are non-mutually exclusive events, which means to calculate the probability of an or happening, I just have to add their probabilities together. So a king, there are 4 kings in the deck out of 52 cards, so the probability here would be 4 out of 52 plus another 4 out of 52 for a total of 8 out of 52, which you can reduce the fraction to 2 over 13. So the probability of that happening is about 2 over 13. If you really, really wanted to put it in as a percentage, you could estimate that the percentage is about 15.38%. A card is chosen at random from a pack of 52 playing cards. What is the probability of a king or a heart? So this is an example of mutually. Excuse me. I wrote the wrong thing on the first one. These are mutually exclusive. So for the first one, excuse me for a second, those are mutually exclusive. So that's why you can just add them together. The second one is the non-mutually exclusive. These are the ones where they can have some overlap. So I apologize for my error. Please go back and correct what you wrote down, guys. For this one here, we have to add the probabilities. So there are 4 out of 52 kings. So four kings out of 52 cards. Plus, there are 13 hearts in the deck out of 52. However, okay, and this comes up first, there is 1 king of hearts that we must take out. There's 1 out of 52. So the probability, if you just go along the top, 4 out of 13 would be 17. Take away 1 is 16 out of 52, which we could reduce to 4 out over 13. And if you wanted an estimation of percentage, we could calculate the percentage of that to be about 30.77%. Okay, let's do some more examples. 2 fair dice. Okay, so 2 fair dice are thrown. Fair dice just means they're not rigged to show up on a certain side. And a standard die has 6 outcomes. What is a probability that the score on the first die is a 6 or the score on the second die is a 5? Okay, so these are non-mutually exclusive events. Okay, so these are non-mutually exclusive events. It is possible for the die to show up as a 6 and the second one to show up as a 5 together. So what we're going to do is in scenarios like this, when we want to calculate total possibilities, there are 6 times 6 outcomes. Okay? If you are talking about successive numbers of outcomes in total, there are 36 here. 36 outcomes. Because for each outcome on the first die, like if you roll a 1 here, there's 6 ways that the second die can show up. If you roll a 2, then there's 6 more, so you have 12 total. If you roll a 3, there's 6 outcomes on the second die. That's 18, and so on and so forth, until you've exhausted all of them. So if the probability on the first die is a 6, so we need a 6 set on the first die, and then there are 6 outcomes that could happen on the second die. So that would be 6 over 36. And then the second die, if it turns up a 5, there are still 6 other ways the first die could show up. So 6 out of 36 for both of those. You're going to add those together. But then there is exactly one way that the die roll could show up a 6 on the first die and a 5 on the second die. So we have to take out 1 over 36 outcomes. So you get that P is equal to 11 over 36. So 11 divided by 36 gives us that the probability would be approximately 30.56% of having either a 6 on the first die or a 5 on the second die, but not both. The next event. A card is chosen at random from a pack of 52 playing cards. What is the probability of picking a king or a heart? Well, it turns out that I duplicated the problem from before, so I'm not going to do it again. See the previous page here. Oops. It seems like I just kind of copy-pasted by accident. See the previous example. King or a heart. See previous page. Whoops. Okay, so there are 30 children in a class, and they all have at least one cat or a dog. 14 children have a cat. 19 children have a dog. What is the probability that the children at random have both a cat and a dog? So this is going to be non-mutually exclusive again, and we're going to be using the formula in a slightly different way. Okay, so there are 30 children in a class, and they all have at least one. So we know that the total probability here, 30 over 30, is equal to 14 children having a cat. So the total here, trying to just write out everything, is equal to the cats plus the dogs. So the dogs is 19 over 30. And then you have to subtract the overlap, because we're looking for, whenever we have non-mutually exclusive events, you always have that probability of overlap. So we don't know. That's what we're looking for. What is the probability that they have both a cat and a dog? That is the overlap. So x over 30. So because we're just adding fractions here, none of these 30s on the bottom matter. So we basically just need to solve the equation on the top. So we have 30 equals 14 plus 19 minus x. So we get 30 equals 33 minus x. Subtracting 33 from both sides, I get negative 3 equals negative x, which then dividing by negative 1 on both sides, x equals 3. So x equals 3 here. So what is the probability of choosing a child at random that has both a cat and a dog? There are 3 children out of 30 that have both. So the probability could be reduced to 1 over 10. And that probability is about 10%. Okay. Next example. In a group of 25 boys, 20 play ice hockey, and 17 play baseball. They all play at least one of the games. What is the probability that a boy chosen at random from the class plays ice hockey but does not play baseball? So we're going to use the same formula that we did before because these, again, are non-mutually exclusive events. So the total 25 over 25, because the total is going to equal, we're going to put H for hockey plus B for baseball minus both. So we've got 20 out of 25 play hockey. We've got 17 out of 25 play baseball. And we're looking for the probability that, or we need to find how many play both, which is X out of 25. So just like in the previous example, we're going to use the equation on the bottom. So 25 equals 20 plus 17 minus X. So I get 25 equals 37 minus X. So you get negative 12 equals negative X. So as you saw before, then that means X equals 12. So there are 12 boys that do both. So 12 that do both. So what is the probability that a boy chosen at random from the class plays ice hockey but not baseball? That means out of the 20 that play hockey, so 20 play hockey, we have to start with that. And we need to take out the 12 that do both. That leaves 8 for only hockey. So we take the 8 and we put it over the class of 25. And the probability of that happening as a percentage would be just about 32%. Just about 32%. All right, guys. So that's it for mutually exclusive events and mutually non-exclusive events. Remember that mutually exclusive events are two events that cannot happen together, like turning left and right at the same time. Mutually non-exclusive events can happen at the same time, like drawing a red heart from a deck of cards, because hearts can be red, and they are. And then we use slightly different formulas to calculate the probability of these events happening together. So that's it for today's video, guys. Thanks for watching, and I'll see you in the next one.